Okay, so today we are going to be looking at motor calculations, and it's on page 186 of the supplemental text. So that's what we're doing. Prior to that, we did everybody got a motor starter, and those of us who were here, and everybody got credited with 20 points that were here on homework assignment number 8. So that was today's reward for being in class and also for being able to take apart and put back together a motor starter. So now we're into motor calculations, and this is from a 2004 from EC&M and Mike Holt. So the guy that did all this stuff is the guy that does the quizzes that you see. And so what we're interested in here is what you just took apart is this part right here. This is the part that you took apart right there. That's the contactor, okay? Now that's the symbology right there is for the contactor. Now we're going to talk about symbology later, but that's what you took apart. Now you have 3 instead of 2. There were 3 in your case. There's 2 in this case. But downstream from that are the overloads. And you saw the overloads. You got an idea what the overloads are. Now that's for the long running, those take a long time to heat up, but when they heat up, they'll turn the motor off. Okay? They'll turn off the control circuit, which turns off the motor. Also, ahead of it is the breaker or the short circuit, whatever that is, overcurrent protection that does when the motor starts. This is the guy that protects it. This is the guy that protects it. And then we're going to look at that, and we're going to say now what do we have to do here? Okay, so basically, the best method for providing overcurrent protection for most circuits is to use a circuit breaker that combines overcurrent protection with short circuit and ground fault protection. However, this isn't usually the best choice for motors. With rare exception, the best method for providing overcurrent is to separate the overload protection from the short circuit and ground fault protection devices. So that is what we're going to do. We're going to look at what's ahead, what you would put ahead of the motor circuit. I've never done one where they're together. I've never done that. Although with low current applications, they can be, but most applications, they can't be. Motor overload protection devices like heaters, which is what you took apart there, protect the motor control equipment, and the branch circuit conductors from motor overload and the resultant excessive heating. They don't provide protection against short circuits or ground fault currents. That's the job of the branch and feeder breakers, which don't provide motor overload protection. This arrangement makes motor calculations different from those used for other types of loads. And let's look how this is going to work. So here's overload protection. There is the breaker, and it's usually a separate device. It's not housed right on top of, it's something separate. You'll have a breaker, then you have wiring down to the starter. Okay, so they're not interconnected. Okay, now some people have connected the two together, but usually they're not. Okay, so that's that. Okay, if you use fuses, you must provide one for each ungrounded conductor. Thus, a 3-phase motor requires 3 fuses. Keep in mind that these devices are at the load of the branch circuit and that they don't provide short circuit or ground fault protection. Motors rated more than 1 horsepower without integral thermal protection, and motors rated 1 power or less are automatically started must have an overload device sized per the motor nameplate current rating. Now that's why we studied about nameplates, so that you get that out off of a nameplate. Okay. You must size the overload devices no larger than the requirements of 430-32. Motors with nameplate service factor ratings of 1.15 or more must have an overload protection device size no more than 125% of the motor nameplate current rating. So if you see the service factor 1.15, you can't go bigger than 1.25. Most of the time, you don't go 1.25. Why? How do you size a motor overload? If it says full load amps 31, what do you size the overload to? 30, I said 31 is the full load amps. So you look at the nameplate and it says 31 amps. What are you going to size the overloads to? You can't go over 125%, but are you going to size them at 31? No. You're going to size them at 35? I doubt it. You're going to go 32, 30, 33, something just a little bit over, but not much. Why? Because this is slow moving thing, but if they get dusty and old, you want them to stop when they get at some point. And that where they stop is usually just a little bit above, okay? Now you can go 35. There's nobody saying you can't, but your motor probably break up on you before it gets to 35. Does everybody follow that? You can go 2 or 3, but don't go hog wild and go to 10. Don't go to 40 or don't go to 38 or 30, whatever. Go a little bit above, but not. And here's where it gets interesting because some people say, yes, you should. He's all wet. You should at least go to 36 or 37. You understand that as long as it's running normally, it's at 31. When it starts to get old and starts to deteriorate, it starts to move up. And it doesn't take much for it to start really getting in bad shape. So do you want to trip it at 32? Do you want to trip it at 33? Those are good values to start thinking about. If it gets much more than that, then all of a sudden you're I don't know. There's no rule that says other than 125%, but you got the idea. It's something that you have to figure that out and you have to size them. You're responsible for sizing these, or otherwise, what happens when you start the process up? You'll have intermittent trips. If they go above, if it's sized for 31 and you've got a 30 in there, daggone, the thing will trip. It may not trip immediately, but it'll trip. Okay. Now, if you undersize the load, or if you oversize, in other words, if you say the load is 25 horsepower and it's 31 amps or whatever, and it really is a 15 horsepower load, now the ampacity is going to come down. So if you don't size the load properly, the ampacity is going to come down less than the full load amps. But do you still size it at 31 or 32? Yes, you still size it at the full load amps of the motor. Okay. So that's why it's important to size the load. Okay, so here's an example. Suppose you use a dual element fuse with overload protection. What size fuse do you need for a 5 horsepower 230 volt single phase motor? The service factor of 1.16 if the motor nameplate is 28 amps. Okay, so now you get to play the game. And here they give you the answers. So you don't have, guess what? This gets you deeply into this. Why? Because there are so many stinking rules. And I guarantee you, so if you don't know where this stuff is at in this code book, you're dead, because every one of these is different. Every one of these has different little nuances to it. So my goal today really is to get you involved in looking this code book thoroughly, because all of a sudden you say, oh, there's about 1 million combinations of how you can do this. And that, yes, there is. Okay, so here you're going to be looking for all this stuff right here: 430.6, 430.32, 430.55. Okay, here's your answer. All right, it's no more than 125. Okay, that's 28 times 1.25 is 35. Okay, so there's your answer. Bless them. But here are a number of examples. Like, here's another one. Okay. Nameplate temperature rise of 40 degrees or less. No less. Okay. Here's another example. You follow what I'm saying? Okay, so you have to read through these in their entirety. You can't short circuit this. You have to get in a code book, and that's why I brought the code books along with me today. Okay, again, suppose you're using a dual element fuse for an overload protection. what size fuse do you need for 50 horsepower, 460 volt, three-phase motor? And by the way, when you're using fuses, what else do you have to protect against? Single phasing. So if one of the three fuses blow, the motor will still run on single phase, but the motor will eventually burn up if it doesn't, if you don't have your heaters set correctly. So you have to guard against single phasing. And most of the fuse blocks today, if one fuse blows, it will know and will shut you down. So it'll give you a contact off of them that one fuse blew, and therefore you have a contact from them that says it will shut you down. So again, if you've ever heard the word single phasing, that is a bad thing. That's why at Owens Corning, we never used fuses. We always used a circuit breaker, MCPs, motor circuit protectors with circuit breaker overload, with a circuit breaker capability. So motor circuit protector with a control with a CB, MCP CB, motor circuit protector with a current with a circuit breaker in it. So basically, that's what we always use, motor circuit protectors. And those were rated at 65K amps, which is what you would get in any SCCR rating. So you would always go to 65K for your short circuit current rating, SCCR rating of your panel, okay, or of your motor starter. All right, so here is an example. Again, you're using a dual element fuse for overload protection. What size fuse you need for 50 amp, 50 horsepower, 460 volt three-phase motor that has a temperature rise of 39 degrees and a nameplate current rating of 60 amps, full load amps. Okay. All right, so let's look at this one and see if we can figure this one out without looking at the answer. Okay, the motor circuit. Okay. Okay, so not the motor full load current, a size per motor nameplate current rating. So here's one of those situations where, again, you get a starter, you get a motor, you get a 50 horsepower, but you get the amps. So now you always have to use the amps. Okay. Now, some motors are rated not in horsepower, but they're rated in kW, okay? So if you have a motor that does not have horsepower, but you have kW, what is the conversion factor?
0.746.
0.746, very good. Okay. Right, that's exactly it, okay? So that gives you, there's only three numbers you need to remember in electrical work. Square root of 2, square root of 3, and 746. Those are the three. What's the square root of 2 good for? Peak versus RMS value, right? For voltage or current. What's square root of 3 good for? Converting for three phase. What's 746 good for? Right here, right there. Okay, the only three numbers you need to remember. Everything else comes out of a book or whatever, but these three you need to kind of have, as they say, in your back pocket. Okay, enough on that. But, okay, so here's 75 amps. Overload protection shall not exceed 75 amps, so you can use a 70 amp dual element fuse. Okay, that's what they did. Okay, motors that don't have a service factor rating of 1.15 must have an overload protection size not more than 1.15 or 115% of the nameplate rating 430-37, which is, okay, so that would give you, the answer to this one was D. But again, okay, so let's go to the next one. So here, you get it? Are you getting there?
Yeah, I think I'm missing a screw.
That's okay.
I'm not sure.
That's all right. There's a few laying around over there, but that's okay. Don't worry about it. Those starters have seen their better days. So. And by the way, the starters that you'll see today, these are NEMA starters, and you'll see IEC starters today almost exclusively. And they're a little smaller, but they do the exact same thing. They all do the exact same thing. All right. Single branch circuit conductors. Branch circuit conductors that serve a single motor must have an ampacity of not more than 125% of the motor's full load current, as listed in Table 430-147, blah, blah, blah. So you must select the conductor size from Table 310 according to the terminal temperature rating 60 to 75 degrees of the equipment. Let's reinforce this by working through an example. What size THHN conductor do you need for a 2 horsepower, 230 volt single phase motor? All right, so here you look at what's the current size. All right, so the conductor cannot be less than 125% the full load amps of the motor. Full load current, full load amps, okay? This is nameplate. So full load current of a 2 horsepower motor, single phase, is 12 amps. So 12 amps times 1.25 is 15 amps, and there you go. All right? These are simple. Now, and what's the size of the wire you need for 15 amps? 14 AWG. Again, and again, many people will require that you use 12 for anything for power. So you might want to use 12 instead of 14 AWG. So that's another local code thing you might actually have to abide by, so you got to be careful there. Okay, short circuit and ground fault protection, section 430. Short circuit and ground fault protection device for fast current rise. Here's another one. The size of the short circuit and ground fault the motor branch circuit, except as it serve torque motors, so they're okay. All right. So here is actually talking about sizing of the breaker. All right. Short circuit ground fault protection device. So how big is it? How big do you protect by? That's the question, okay? So if you go, here's one of those times when you can go all the way up to the maximum rating, which is usually way too much. But you want to go more than the full load when it starts. So this is how a motor starts. The ampacity goes way up, and then it comes back down, and then it's level for the rest of its life. Okay, as long as you have a constant load, it's level like this. But you want to pick something up here, but not way up here. You want to pick something that's higher than this, but what is this? You don't know. Okay, so you have to look at your type of breaker and time delay, whatever. So you need a non-time delay. You need a non-time delay fuse. Why do you need a non-time delay fuse? If you're going to use a fuse, why is it a non-time delay? Because that fault comes quick. It's a quick. This happens in if you have a fault. Your fault will be like way it'll go like this. It'll go like that. All right. It happens very quickly. So a non-time delay, you cannot have a time delay fuse. Okay, you shouldn't have a time delay fuse. If you did, it does not protect against a fault. All right, so, and by the way, I'm looking at 4 individuals who will probably do this. Size these things and have to come up with the right combinations. All right, if you work in industry, you will do this a lot. I did it, and I'm not special. I had to do this. Everybody has to do this because if you're working on a process and you're assigned to buy the equipment and put it in and make it work, you have to size this breaker so that it will allow the motor to turn on. It's higher than this, but it will hopefully withstand a fault. You will have to buy these, okay? All right, so again, horsepower, 115-volt single-phase motor shall not exceed 110 amps, okay. All right, so, all right, so here's some, which is the right one? I don't know which is the right one. I don't really know. This one is true. This one, number 2, is true. And this one, number 3, is true as well. So again, you have to look at the table. You have to see which ones allow, what is allowed, and you have the next highest one is what it boils down to. Use the next highest one. All right. And you must size the conductors at 125% of the motor flow current. You must size the overloads no more than 115% or 125% based on the conditions, okay? You must size the short circuit ground fault protection device from 150% to 300% of the motor full load current. All right, so this is the range of where this goes, but you have to size it someplace in there. And how you do that is up to you. All right? And this one is another one. Same thing, same song, second verse. And again, I don't want to bore you with these, but like I said, when we have our final test, I'm going to put 2 or 3 of these on there, and you will have to look it up in the book, and I'll lend you one if you don't have a National Electrical Code, I'll lend you one, and then you can take it and use it. But basically, you can bank on it'll be just like one of these. I'm not going to vary from it very much, but I'm going to jazz it up a little bit, but not trick you or nothing like that. I want you to be able to do that, okay? Now, he went through and he did another one as well. So he did 2 of these in 2004, and this is on motor calculations feeders. And so this has to do with the feeding of what does it take to get power to the motors and all that kind of stuff. So this is now concentrating on these wires, okay? By the way, when you size the wires that go to, if you size the wires, let's say you add a capacitor, okay? If you say, I've got a motor and I've got a capacitor, and I size that, do you size it based on the wire of the full load amps here, or with the efficiency improved because of the capacitor? Do you size the wire based on this or the combination of these? It's a trick question. You size it based on the full load amps of the motor. Why? Because the capacitor has a fuse. What happens if the fuse blows? All of a sudden your ampacity goes up and your wire would overheat, and you would have a mess. So you have to size the wire to the motor, even though with the motor and the capacitor you drop the amps. Okay, does that make sense? Because that's exactly what happens. Now, when you have a motor and a capacitor, do you size the overload to the new motor and capacitor, or do you size it to the motor full load amps? Another good question. The answer is I don't know. You have to figure that one out yourself. But you see the reason for using because capacitors have a fuse. If a fuse blows, all of a sudden your current goes up. Okay. Does anybody have any questions about this at all? Ready to call it a day? As soon as Mr. Fent gets through with putting his back together again. Are you about done?
Yeah, I missed the contact.
Oh my goodness. Oh my. Well, I think we've hammered this enough. I don't want to belabor this, but I want you to understand that this gets into a bunch of nif-naf stuff, but it does require you to go into these sections and read this stuff, and you will get good at the National Electrical Code. I can predict you. I'm looking at 4 people here who will get good at using the National Electrical Code for this kind of stuff. But again, this is, I'm not just trying to make you think that I know all this stuff forwards and backwards, because I don't anymore. I used to know it very, 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 very well. And I know what I had to do was I had to go back and read this 2 or 3 times, each of these sections, in order to get it right, because you have to size the wire, you have to size the breaker, and you have to size the overloads, or it will not, and the capacitor, or it will not work. You'll sit there and people will be smiling at you and say, "Why is your motor tripping out?" And you say, "I don't know." And they'll say, "Where do you go to school?" You say, anywhere, but no, don't, you don't have to say that. Just say, "I know it, but I forgot." Okay? So that gets you through page 199, and I promise you that I'm not going to bore you with this. But on the other hand, I want you to understand that this is for real, and it does take time, and I won't vary from these questions very much at all. But I can sit here and ask you questions, but you should know where this is at in the National Electrical Code, and you should not be afraid of the National Electrical Code. And you should also know that you're going to have to do this. That's my basic point today, is you're going to have to know that you're basically going to have to do this. Has anybody done this stuff before? Any of you size these? Nope. Has anybody sized a motor starter and breaker and wire size and all that? You have. Okay. All right. But that's a responsibility. It's part of your job. It'll be part of what you have to do. So again, I don't want to beat you up with this, but that's what I'm going to have. A question on a test, or 2 or 3 questions on a test about this kind of stuff. Okay. Any questions everybody's got? Everybody get their stuff? Did everybody get everything back that was handed in? Anybody have any questions of me? All right. Well, you're dismissed. Except for Mr. Fent. He gets his act together and gets that done.